Swayam Prabha. Digital India. Educated India.
Welcome to the fifth lecture of the module Spur Gear and Design of Spur Gear. In this we will study the leftover part of the design of spur gear under surface fatigue phenomena, and thereafter we will compare the factor of safeties based on bending fatigue of the gear tooth of a spur gear and surface fatigue of the spur gear. Thereafter, we will start a new module that will be for helical gear and design of helical gear. So, let us first review the surface fatigue phenomena which we studied in our fifth lecture, and then we will continue that to the end of the design of spur gear under surface fatigue phenomena. The Hertzian contact stress which we studied in the previous lecture was given by sigma c is equal to Wt, which is the transmitted load, F is the face width, dP is the pitch circle diameter of the pinion, multiplied by 1 divided by pi 1 minus nu p square. Nu p is the Poisson's ratio of the pinion, divided by Ep, which is Young's modulus of the material of the pinion, plus 1 minus nu g, where nu g is the Poisson's ratio of the material of the gear, square divided by Eg, Young's modulus of the material of the gear, multiplied by cos phi sin phi divided by 2 and mg divided by mg plus 1, where mg is the gear ratio given by number of teeth on the gear divided by number of teeth on the pinion. Well, now when we see the equation of Hertzian contact stress which acts between gear tooth in mesh, then we have some term which are function of only material property, like the term within the bracket. It will be taken separately, and the term which are related to the geometry, that means number of teeth on the gear, number of teeth on the pinion and all, and the pressure angle. So, clubbing the material property into one group, we have a term known as elastic coefficient, which is 1 under root 1 divided by pi within the bracket 1 minus nu p square divided by Ep plus 1 minus nu g square divided by Eg. For commonly used gear materials, the value of Cp can be found from a table which is given in the next slide. So, after substituting the value of Cp in the equation of contact stress sigma c, we have this term, this all term under root, this will come outside, it will be taken as Cp, and then Wt, dP, F and this term. Now we will take this term which is a function of geometry, that is so the Cp is determined from this table, can be determined, we studied it in our previous class also. Then the geometry factor I for fitting resistance is given by this term. So, this I is cos phi t sin phi t, This phi t is actually phi for the case of Spur gear, phi t is equal to phi. When we will study helical gear, then it will be separately called as a transverse pressure angle. Then this I is cos phi t sin phi t divided by 2 mn, where mn for Spur gear is 1 multiplied by mg divided by mg plus 1 for the external gear and minus 1 for the internal gears. Then after substituting the value of elastic coefficient and the geometry factor for the pitting fatigue, the Hertzian contact stress equation is given by Cp under root Wt divided by Fidp. Now in this equation again some factors have not taken into consideration, that means the overload or the dynamic effect or the mounting and the size are not taken, similar to the bending fatigue in the Lewis bending fatigue equation. So in this case also some correction factors are used and they are called Cv in place of Kv. In the case of bending fatigue, that was Kv. Now it is called Cv, but both are same and determined in a same way. Similarly, CO is the overload factor, and this will be similarly obtained as the overload factor for bending fatigue was determined, the mounting factor and the size factor. Now after determining the surface contact stress which will act when the two gear tooth will be in contact, now we will find the surface fatigue strength for gear materials. Now the surface fatigue strengths are given in the literature or in the data books, and they are given by AGMA, the American Gear Manufacturers Association, and those data are again for certain set of conditions. Now if you want strength for the condition under which your gear has to work, you have to multiply the surface fatigue strength data obtained from literature by some factors, and those correction factors are again the life correction factor, hardness ratio correction factor, then the temperature factor and the reliability factor. In the case of bending fatigue, this hardness correction factor was not there, as we are studying contact stresses, and so the hardness of surface of the pinion and gear will be an important thing, and therefore this hardness correction factor is used in the case of determination of surface fatigue strength. Now surface fatigue strength SFC dash can be obtained from the literature, and one of the table is given here, very much similar to the table for SFB dash for bending fatigue strength. Here also for different category of materials and for different AGMA class and material designation and under different heat treatment condition and minimum surface hardness condition, the surface fatigue strength in megapascal is given, and it is given in the form of range. So for any particular material you can select the value in between the range given here. Here a graph is given for grade 1 and grade 2 through hardened steel. Knowing the Brinell hardness of the surface, you can use this figure or the equation given here to get the value of SFC dash. If it is grade 1 material, then the value of SFC dash, surface fatigue strength of the material, may be obtained either from the curve 1 or by the equation 2.22 Hb, where Hb is the Brinell hardness number of the material of the gear plus 207 megapascal. Similarly, for grade 2 material, the curve 2 or the equation given by 2.41 Hb plus 237 megapascal can be used, where Hb is the Brinell hardness number of the material of the gear. Similarly, for different other materials, you can use data books to get the SFC dash. Now, the life correction factor, similar to the life correction factor for the case of bending fatigue strength KL, here also if the life is 10 to the power 7, then this SFC dash is given for 10 to the power 7 number of cycle, and so the factor CL is equal to 1. For other life, you have to find the value of CL and you have to multiply this SFC dash to that CL to get the value of strength SFC. Or you can use this formula also to get the value of CL. Now, the hardness ratio correction factor, which was not used in the surface bending fatigue strength, the pinion generally has a smaller number of teeth, because in the gear mesh, the smaller gear is called the pinion. Okay, this is the pinion and this gear. Pinion has a smaller number of teeth, and so for any revolution, let the RPM of the gear is Ng, RPM of the pinion is Np. So, we know that the Np divided by Ng will equal to omega p upon omega g, and it will be in the inverse of their pitch circle diameter. Now, pitch circle diameter of the gear Zg divided by Z pinion. Now, this is more than 1, because this is the ratio Zg divided by Zp, so it will be more than 1, and so Np will be Ng multiplied by a number more than 1, and so Np will be more than Ng, it is obvious. So, the pinion generally has a smaller number of teeth subjected to more cycles of contact stress. Now, as it is rotating with more RPM, and so it will be subjected to more contact stresses. If both the pinion and gear are through hardened, then a uniform surface strength can be obtained by making the pinion harder than the gear. A similar effect can be obtained when a surface hardened pinion is mated with a through hardened gear. The hardness ratio factor CH is used only for the gear. Its purpose is to adjust the surface strengths for this effect, and it is given by a formula, empirical formula obtained through experiments, is equal to 1 plus capital A within the bracket mg minus 1, where mg is the gear ratio and it is equal to Zg divided by Z pinion, and capital A is found from this condition: if Hb of the pinion, means Brinell hardness of the pinion divided by Brinell hardness of the gear, is less than 1.2, then capital A is equal to 0. So, capital A is equal to 0, then Ch will be 1. Well, the meaning is hardness of the pinion is less than 1.2 times hardness of the gear. We had said that to make the strengths equal, we make hardness of the pinion more in comparison to the gear. So, for first case, hardness of the pinion is less than 1.2 of the hardness of the gear. So, hardness of the pinion is less than the 1.2 of the hardness of the gear, then we use A as 0. But if it is greater than or equal to 1.2 but less than or equal to 1.7, 70%, then capital A is given by this formula. And if hardness of the pinion divided by hardness of the gear is greater than 1.7, then A is a fixed quantity and that is 0.00698. Well, knowing the value of A, you can substitute the value of A here and get the value of CH. For surface hardened pinions which are greater than 48 Rockwell C scale RC 48 run against through hardened gears, we have CH, the hardness correction factor given by 1 plus capital B within the bracket 440 minus Brinell hardness of the gear, where B is given by 0.00073 e to the power 0.052 RQ, where capital RQ is the surface finish of the pinion expressed as root mean square roughness in micrometer. Now, selection of gear material based on contact stress, because the pitting resulting from the contact stress is a different failure phenomena from tooth failure due to bending, and independent specification for suitable material for the pinion and the gear must now be made. In general, the designer must specify the material having an allowable surface fatigue strength SFC more than the Hertzian contact stress which will act on its gear tooth. Now, the factor of safety for bending fatigue will be given by fully corrected bending strength, that means SFB divided by the bending stress. The bending stress is sigma B. Similarly, the factor of safety guarding against surface fatigue NS will be given by fully corrected contact strength, that is SFC divided by the contact stress, that is sigma C or sigma H. Sigma H, Hertzian contact stress which acts between the gear tooth. This is also fully corrected and this is also after taking consideration of all the factors. Now, this NS is equal to fully corrected surface strength, this, and the Hertzian contact stress. Now, if we see the formula for Hertzian contact stress or the surface stress, sigma is proportional to under root of the WT. But if we see the bending fatigue sigma B, then it is proportional to WT. So, if we want to compare the NF and NS, then we have to make both proportional to WT. So, what we do is we just make the square of both the terms and we say it sigma square, sigma surface or sigma C square, it is proportional to WT. Okay. So, while the definition of NS does not interfere with its intended function, a caution is required when comparing NF with NS in an analysis in order to ascertain the nature and severity of the threat of loss of function. That means, we want to find whether the gear will fail by bending or it will fail by surface fatigue. Then what we do is, we determine for the case of pinion and for the case of gear, whatever bending fatigue stress acts, that means sigma B for the pinion and sigma B for the gear. And for the material of pinion and gear, we determine the value of SFB. So, if material is different, then SFB will be for the pinion and SFB will be for the gear. And so, we will get factor of safety NF for the pinion and factor of safety NF for the case of gear. Similarly, for the surface fatigue, we will find the for the case of pinion, the sigma C pinion and sigma c gear. And for the material of these two, we will determine the surface fatigue strength SFC for the pinion, SFC for the gear, and thus we will have NS for the gear and NS for the pinion. So we have 4 factor of safeties. Well, so when comparing NF with NS, NF with NS in an analysis in order to ascertain the nature and severity of the threat of loss of function, when we will compare them, then we see that the sigma c is not linear relationship with WT, but sigma b has. So directly we cannot compare it. So what we do is, to render NS linear with the transmitted load WT, it could have been defined as NS is equal to fully corrected contact strength divided by contact stress imposed square. So NF corrected value is this one, this should not be used. So the value of NSG and NSP will be determined from this formula. So NF is this one and NS is given by equation number C. Well, with exponent equal to 2 for linear or helical contact, or an exponent of 3, this exponent will become 3 for crowned teeth or spherical contact. With the definition of equation C, compare NF with NS when trying to identify the threat of loss of function with the confidence. So these two will be used to determine the factor of safety NF for the pinion, NF for the gear, NS for the pinion, and S for the gear. And the threat will be under the case for which the factor of safety is smallest. So suppose factor of safety smallest is this one, the meaning is the threat is from bending and on the gear. Design objectives for the spur gear. The resulting drive should be compact and small, operate smoothly and quietly, have long life, be low in cost, be easy to manufacture, be compatible with the other elements in the machine such as bearings, shafts, the housing, the driver and the driven machine. Following are the references which were used in the spur gear and design of spur gear. So with this we have completed the spur gears and design of spur gear. The next we are going to our next module, which is for helical gears and design of helical gears. So first of all, we will study brief about helical gear, what is the difference between spur gear and helical gear and its different nomenclatures, and then the design methodology of the helical gear. So let us start the module related to helical gear and design of helical gears. The helical gears are used to transmit motion between parallel shafts. Similar to the spur gear, you see this is a spur gear. The shaft of the gear is this one and the center line of the shaft of the pinion is this one, and both are parallel to each other. Now this one is the helical gear. This is spur gear. Now if you see the way the gear tooth are formed on the spur gear and the helical gear, then it is obvious that the gear tooth in the case of spur gear is parallel to the axis of the shaft. But in the case of this helical gear, where the axes are given by these lines, axes are again parallel to each other, but now the gear tooth is not parallel to the shaft, but it is inclined by certain angle to the direction of the shaft. Well, therefore, what happens in the case of spur gear, you may see that there will be sudden contact between throughout the length of the gear. So, when it will rotate in this way and this is rotating in this way, then when this tooth is coming contact with this one, then there will be sudden contact all along the width of the gear tooth due to linearity. Now, due to this inclination in the case of helical gear, first of all there will be a point contact which will change into line contact, and at the time of disengagement again there will be a point contact. Okay. So, the initial contact of helical gear teeth is a point that extends into a line as the teeth come into more engagement. In spur gears, the line of contact is parallel to the axis of the rotation. In helical gears, the line is diagonal across the face of the tooth. The axes are parallel in the case of helical gear, you see, but the gear tooth are inclined. Now, if you will compare the spur gear, then spur gear will look like this. The gear tooth will be parallel to the axis. But here, for the case of helical gear, they are inclined. Now, similar to spur gear, but with teeth making a helix angle, the angle which makes is called the helix angle. Okay, this is the helix angle. Now, due to this helix angle, what happens is the force is transmitted, or the normal load on the gear tooth will be in this way. It will have two components. One is acting towards the center, which is called the radial component, and another will be axial, which is acting in the axial direction. Okay. Some other component will also be there, that will be the transmitted load. So, in this case, in the helical gear, an axial component is also coming into picture, and so this gear will apply thrust load on the shaft, and so one of the bearing, you see, if it is the shaft, these are the bearings on which the shaft is supported. Now, as an axial load is also acting, one of the bearing must support the axial load also. So, one of the bearing must be a thrust bearing and another the radial bearing, which will support only the radial load. This may be a combination of thrust load and the radial load bearing. Now, a smoother transition of force between mating teeth occurs in the case of helical gear due to gradual engagement and disengagement. In the case of spur gear, all along the width a sudden contact will be there, but in the case of helical gear there will be first contact at the edge, which will convert into a line, and then again point contact. So, there is a gradual engagement and disengagement, and so the operation is very quieter without any noise, very small noise. So it can be run at high speed, it cannot be run for high speed. The gradual engagement of the teeth and the smooth transfer of load from one tooth to another that gives helical gear the ability to transmit heavy loads at high speeds. Because of the nature of contact between helical gears, the contact ratio is of only minor importance, and it is the contact area which is proportional to the face width of the gear that becomes significant. The shape of the tooth in the helical gear is involute helicoid. Involute helicoid means, let we have a cylinder, and on this cylinder a paper is wrapped in such a way that let we have a rectangular paper, and we have wrapped this edge on this one, and so we have, now the paper has become of this shape. Well, now this edge of the paper is here, and this edge of the paper is on this side, and you have wrapped it on the cylinder. This paper is wrapped on the cylinder in such a way this edge A is initially at this point, and this edge B is at this location. Now smoothly you are unwrapping this edge A, or you are just moving this edge A from the surface of the cylinder. Then the locus of A is given by this curve. This is involute. Now if we take number of points along AB line in such a way that it is 1, 2, 3, 4, 5, 6 along this, then all these points will generate a involute profile. Well, so along the length of the cylinder, a involute profile will be generated with certain angle, and that is called the involute helicoid. The surface obtained when every point on the edge, this edge AB, generates an involute is called an involute helicoid. Now here a section of a gear is shown, helical gear, and that is also the parallel helical gear. Well, this is the top view of a gear, and the teeth are shown here. When a section is taken along this, then it is shown in this figure C. When section is taken perpendicular to the teeth, this is the plane BB, which is perpendicular to the teeth. Then that sectional view is shown here. So this is the normal direction, and this is the transverse direction or the tangential direction. Okay. So in the case of helical gear, what happens is, when you will see from this side, along the gear tooth, then it will look like this. Now when you will cut it in this way, then the thickness will be, you see, this is the thickness of the gear tooth when you will see from this side, which is smaller. And when a section is taken in the transverse direction or in the tangential direction, then the thickness is this one. So bigger teeth will look when you will see from this direction. So along the AA, a thicker teeth will be there, and along BB, a thinner teeth will be there. And the pressure angle of these different teeth seen from different direction will be different. Along the section AA, the pressure angle will be given by phi t, and along the normal direction, the pressure angle will be called the normal pressure angle phi n. This is your phi n. This is your phi t. So in the case of helical gear, now we have two pressure angles, phi t along the tangential direction and phi n along the normal direction. Okay. So the pitch seen from the tangential direction along the AA will be this pitch from this distance to this distance will be the pitch in the transverse direction, PT, isn't it? And the pitch, you are viewing the teeth along the normal direction, along this way, is given by this distance, and that is called the PN, normal pitch. And in this figure, it is shown here, this to this is PT, and along the normal direction, this is PN. Well, and the gear teeth are not parallel to the axis. This is the axis. Gear teeth are inclined by certain angle to the axis. Okay. So the angle by which the gear teeth are inclined is known as the helix angle, and that is given by this psi. It is the helix angle. Well, now let this PT, the tangential circular pitch, is this distance AC, small a to small c is the PT. So small AC is equal to transverse circular pitch PT. In the case of spur gear, there were only one circular pitch, and that was called the P, and that was equal to pi d divided by z. Here we have two circular pitch. One circular pitch when the teeth is viewed along the transverse direction, and when it is viewed from the normal direction, BB, and this is PN. Well, so this PN is A to this distance. This is the center line of one gear tooth. This is center line of one gear tooth, and this is center line of the adjacent gear tooth. Well, so from A, a perpendicular is dropped, and this perpendicular is intersecting this line CD line at E point. Okay. So AE is equal to normal pitch PN, and angle ADE DC. ADC is the helix angle psi, isn't it? So, let us define the different nomenclatures. Normal circular pitch Pn is in the plane perpendicular to the teeth. This plane, normal plane, this is the normal plane, and this is the transverse plane. Transverse plane. Okay. So, Pn is equal to Pt cos psi. It is obvious. This angle is psi. So, this is 90 minus psi and this is psi. This angle is psi, helix angle. So, AC cos psi is equal to AE. So, Pt cos psi is equal to Pn. Pn is equal to Pt cos psi. Well, and the distance AD is called the axial pitch. Another term is coming. Axial pitch Px is equal to AD. Well, now this AD you can find in terms of this Pt. Tan of the psi is equal to AC divided by AD, and thus AD is Px. So, Px is equal to Pt divided by tan psi. Now, normal diametral pitch, that means the diametral pitch Pn, this Pn will equal to Pt divided by cos psi, or the module Mn, normal module, because we know that the shape of the gear tooth viewed in the normal plane and in the transverse plane are different, shape are different, and so their module will be different. So, the module of the gear tooth in the normal plane is called Mn, and the module of the gear tooth in the transverse direction is M or Mt, both are called M or Mt. Now, in which view the true shape will be visible? In the normal plane, the true shape will be visible when you will see from this direction. When you have taken section along AA and you are viewing the teeth, then it is not the true shape. So, true shape is this is represented by Mn, not by Mt. So, Mn will be Mt or M or Mt divided by cos of the psi, and Pn multiplied by Pt, Pn multiplied by Pn, the normal pitch, this Pt cos psi, and capital Pn will be this, and this will be cancelled, you will get the pi. Now, some relationships, that means we have helix angle, we have a normal pressure angle, we have tangential pressure angle. So, what is the relationship between them? That can be obtained from the force diagram on the helical gear. Here a helical gear is shown, they are the tooth of helical gear, different teeth. This is the pitch cylinder. Tangent to the pitch cylinder, whatever load will act will be the tangential load Wt. Now, to determine the forces, we have drawn an infinitesimally small element, and that is represented by this one, this. Let me call it A, B. B is the point where the load is acting on a gear tooth. A, B, C, D, then E, F, G and H. Well, so AB is the tangential direction AB is the tangential direction and CB is towards the center of rotation of the gear, and so it is the radial direction. CB is the radial direction and GB is along the axis, along the z direction. Well, and so it is the axial direction. Okay. Now in the plane of ABCD, the direction DE is the direction in which the normal load acts in the case of spur gear. So DB is the direction of normal load Wn for spur gear. Okay. Now in the case of helical gear, the gear tooth, this gear tooth is not parallel to the axis, but it has rotated by an angle psi. So the plane of Wn for the case of helical gear will make an angle psi with the plane on which Wn for spur gear acts. It means the ABCD plane will make an angle psi with the plane on which Wn for helical gear will act. So let that plane is EFBC. EFBC. BC is the plane where normal load Wn acts for helical gear. Okay, so this is this plane. This is the plane. And the angle between plane ABCD and plane EFBC is psi, and that is shown here. This is psi. Okay, this is the Wn for the case of helical gear. Now the pressure angle is represented by an angle which it makes with the horizontal plane, and that is this one. This is the pressure angle phi n. The tangential phi you can get from the Wn for the case of spur gear will act from D to B. From D to B, Wn for spur gear will act. Wn for spur gear. This is Wn for helical gear. Okay. So the angle DBA will be the pressure angle phi for the case of spur gear and phi t for the case of helical gear. Both are same, phi or phi t. So now you have phi t, Wn for the case of helical gear, Wn for the spur gear, and the helix angle equal to psi. So from that you can get a relationship between between psi and phi n and phi t, and that is cos psi is equal to tan phi n divided by tan psi t. Tan phi n is given by tan phi n is EF divided by FB, and tan phi t is equal to dA divided by AB, and it is clear that dA is equal to EF, dA is equal to EF. So, this and this will cancel and you will have AB divided by FB, AB divided by FB. Now, what is A? Where is AB? This is AB divided by FB, this FB, isn't it? This is 90 degree. So, you can take the triangle AFB, and in this AFB your AB this AB divided by FB, where is the FB? This FB will be your cos psi. So, this is equal to cos of the psi. Normal module Mn is empty divided by cos psi. It is, we have already studied it. For the case of parallel helical gear, we have seen that the teeth are inclined by certain angle, and that angle is called the pressure angle. So, when along the normal plane actual gear teeth is visible, then we take it as a virtual gear, and number of teeth on that is called the virtual number of teeth. So, viewing from along the teeth, the apparent pitch radius is greater than when viewed along the shaft. When you view from along the shaft and view along the teeth in this way and in this way, the pitch radii will be bigger for this case. The greater virtual radius R has a greater virtual number of teeth, and that is given by Z dash is equal to Z divided by cos cube psi, allows fewer teeth on helical gears without undercutting, and that is shown here in this figure, where a section along the normal is taken and the major axis and minor axis, you see this one, this is the ellipse. The surface will look like an ellipse with minor major axis given by small a, and the minor half minor axis given by b, okay, and this b is equal to d divided by 2, the pitch circle diameter divided by 2, and this a is given by d divided by 2 cos psi, d divided by 2 cos psi. So, this is d divided by 2 cos psi, like that. So, what we say that when we have taken this normal section, a gear tooth which is visible along the normal plane is this one, okay. So, if at this point the radius of curvature is r dash, then r dash is given by a square divided by b. Substituting the value of a and b, we get the r dash is equal to 2 r dash is equal to d divided by cos square phi, okay. This is psi. So, z dash, what we do now is, with this radius a gear is made, with this pitch radius, pitch circle radius, a gear is made. This is the virtual gear, okay. Now, on this virtual gear, the number of teeth which with normal pitch equal to Pn will be given by z dash 2 pi r dash divided by Pn. Substituting the value of Pn and R dash, we get Z dash is equal to D divided by Mn cos square psi. But D, the pitch diameter of actual gear, is given by number of teeth on actual gear Mn divided by cos psi. Now substituting this, we get Z dash, this Z dash, virtual number of teeth on a virtual spur gear. This is the virtual spur gear. Virtual spur gear is Z divided by cos cube psi, and that will be more than the actual one. This is an example in which for a helical gear, normal pressure angle is given, helix angle is given, and the transverse diametral pitch is given, and number of teeth are given Z. Then the pitch diameter, transverse normal, axial pitches, normal diametral pitch, transverse pressure angle are determined. So D is equal to number of teeth multiplied by Mn. Number of teeth is 24 multiplied by the normal module, which is 3, transverse module, which is 3, and so the pitch diameter is given by this one, and the transverse pitch is pi multiplied by mt is this one. Similarly, the Pn is determined, then Px is determined, Mn is determined, and phi t is determined. Now the interference with helical gears, similar to the spur gear, there will be interference in the helical gears also, because they are made by involute profile. So minimum number of teeth on the pinion can be obtained from this. K is equal to 1 for full depth and K is equal to 0.8 for stub teeth, similar to the spur gear. And on spur meshed with larger gear, with gear ratio mg is equal to number of teeth on the gear divided by number of teeth on the pinion is equal to m, the smallest number of teeth which will not have interference is given by this formula. The largest gear with a specified pinion that is interference free is this one. Smallest spur pinion that is interference free with a rack is this one. Now the force analysis. We have already studied the planes and the normal force which acts in the case of helical gear. This is the direction in which the normal force acts. When we take component of this Wn in the transverse direction, means tangential direction, the radial direction, and the axial direction, then we get the transverse load Wt on the helical gear, radial load Wr, and the axial load Wa. With the sin phi n and this psi, we get the Wr, because in this we had taken as A, B, C, D we had taken, and this was E, F, G and H. Okay. So in the plane of E, C, B, F, in the plane of E, C, B, F, this is your Wn, this angle is phi n, and this Cb is the radial direction, you will get Wr. So Wr is Wn sine of the phi n, which is shown here. And thereafter the component of Wn in the Fb direction is Wn cos of the phi. Now this is the component of this Wn cos phi n is taken along AB and BC, and which will provide you the tangential load and the axial load. Now W is W is determined in terms of transmitted load, because transmitted load is the known load. from the power which you want to transmit at the pitch circle diameter dP at the RPM NP, you will get the value of Wt. So Wt is known. So from Wt we get the value of this Wn. Wn is equal to Wt divided by cos phi n and cos psi. It is substituted here. Then you get Wr, Wa and Wn all in terms of transmitted load and the transverse pressure angle, helix angle. So with this we have completed the first lecture for the helical gear, in which we studied the difference between the spur gear and helical gear and different nomenclatures related to the helical gear, like when the helical gear will be viewed in the tangential plane, the transverse plane, or along the normal plane. Then the normal pressure angle, the tangential pressure angle and helix angle were identified. Thank you.